Hello everyone, welcome to the presentation for our work investigating the effect of language models in sequence discriminative training for neurotransducers. I'm Zijian Yang from RWTH Aachen University. In this work, we investigate the effect of language models used in sequence discriminative training, including different language model label units, such as phonemes and words, and the different language model context sets. A systematic comparison is conducted across different hypothesis space generation methods, including lattice-free and embedded list approaches, as well as different training criteria, including maximum neutral information and the minimum base risk. In this work, we employ the strictly monotonic INT as our acoustic model. The probability of the label sequence is defined as follows. Here, A1 up to S is the label sequence, and Y1 up to T is the alignment, and B is a collapse function. In this work, we always use a phoneme as the label unit for the transducer. Furthermore, we also employ a limited context dependency to further simplify our acoustic model. In this work, we mainly focus on the maximum mutual information criteria for sequence discriminative training. The MMI objective is defined as follows. Here, QSEC is the product of the acoustic model and the language model probabilities. Here, the numerator is equivalent to a standard cross-entropy loss for INT models, and the denominator is the summation of probabilities of all possible sequences. To compute the denominator, one can directly use a lattice-free manner approach or use a best-list approximation. When the language model has the phoneme as the label units, it's quite convenient to do a lattice-free MMI training because the acoustic model and the language model share the same label unit. And if the language model has a limited context dependency, it is efficient to compute the denominator by a dynamic programming. Here, this is the definition of the auxiliary function, QTU up to K, which is the summation of probabilities of all the partial sequences that ends with U up to K. And in the recursion form, there are two terms. The first one is for emitting a blank label, and the second one is for emitting true labels. And here QSEC is the combined probability with a limited context. When there is when U equals to the blank, it's only the acoustic model probability with the scale. And when U is a true label, it's a product of the acoustic model and language model probabilities with alpha and beta as scales respectively. Here, when the language model has a full context dependency, it is infeasible to do the recombination. And therefore, we propose an approximation of the context. Generally speaking, we assign a full context C tilde to each pair TU1 to K. And during the recombination step, we choose the context of the label or blank that has the highest score. If a blank has the highest score, we just keep the context unchanged. And if a label has the highest score, we concatenate the label with the chosen context to be the new context. And with this approximation, the language model with a full context, the language model probability with a full context dependency can be computed. And again, this due to this approximation, this new defined QSEC has a limited context dependency, and therefore the DP recursion can be the same as in the limited context case. And when the language model has words as the label units, to reduce the computation complexity, we consider all the possible phoneme sequences, and no lexical prefix tree is used for the word level language models. To this end, we introduce enough word phonemes, and more precisely, for a phoneme sequence, when it reaches the EOW phoneme, we do a pronunciation to word mapping and then compute the language model probabilities on word level. Here, to do the lattice-free MMI training with word level language models, we propose two methods. The first one is the context approximation, which is quite similar to the approximation for the phoneme level language models. However, here language model probability is only considered when emitting EOW phonemes, and moreover, the phoneme contexts are mapped to word context to compute the word level probabilities. And the second method is the pruning recombination approach. Here, it is quite similar to alignment based on the fly beam search. However, we perform a summation of the probabilities in the beam as a recombination step when possible, other than choosing the individual single best hypothesis. And besides, we also apply the multi-level language model decoding approach. That is, when doing the beam search within the word, we use a phoneme level language model, and when it reaches the end of word phoneme, the phoneme level language model scores are disregarded, and the word level language model is considered. We refer our audience to the paper for more details. And here are some experimental results. The first table shows the results of lattice-free MMI training using phoneme level language models with different context lengths. Compared to the cross-entropy baseline, all of the lattice-free methods show improvements on dev order and the test order. With the increasing context size of the language model, the perplexity goes down, indicating a better modeling of the phoneme prior distribution. However, in terms of word error rates, only slight improvements are observed up to 2 gram, and more context beyond that does not yield additional improvements, which indicates a limited effect of the language model context length. The next table demonstrates the performance of the best list approach with various language models used for probability computation in training. Here, the best list is generated with a 4 gram word level language model, and all the experiments share the same hypothesis best list. From the table, we can see that both phoneme level and word level language models show only marginal improvements from longer contexts, which further validates the limited effect of the language model length. Besides, compared to the results in the table above, for example, comparing this full context and diagram case to the table above, the language model is the same, and the only difference is the hypothesis space. Comparing these word error rates, it is shown that even with a respectively small hypothesis space, a good selection of the hypothesis can achieve a performance comparable to using a much larger hypothesis space. Regardless of the context length, using a word level language models are consistently better than using the phoneme level language models. Even using a 1 gram word level language model whose context length is effectively shorter than the phoneme level language model, the performance is still slightly better, indicating that word-level statistics bring more improvements. And comparing MMI and NPR, using both when using the phoneme or word-level language models, the performance are comparable. Then in the next table, the experiments compares the results of MMI training using different approaches to generate the hypothesis space. Here, the word-level language models used for hypothesis generation and for probability computation in training can be different. So here, training LM refers to the language model used for probability computation. And as shown in the table, when the hypothesis space is good, namely generated by the foreground language model, using a foreground language model for probability computation provides marginal improvement compared to using a one-gram language model. However, comparing the models using 1 gram and 4 gram in hypothesis generation, there is a large gap on performance, which highlights the critical role of the hypothesis space quality in the performance. When using a 1 gram for hypothesis generation, the insertion error is much larger. This is because of a biased error pattern in the hypothesis space. We refer the audience to the paper for a more detailed analysis. And among these different hypothesis generation approaches, the Proning recombination method obtains better performance because of a larger probability mass due to the summation of the hypothesis and as well as the better hypothesis space generation because the phoneme language model is used during training to help the search process. And the next table is a subset of the experiments above with a stronger transformer language model. And the results here the results here shows similar conclusions as the table above. And so here are our conclusions of this paper. First, we see that word-level language models performs better than phoneme-level language models when a good hypothesis space is applied. And secondly, the context size of the language model used for probability computation in sequence discriminative training has a marginal effect on the performance. And last but not least, the quality of the hypothesis space for sequence discriminative training is critical for the performance. And that's all for our work. Thanks for your attention.